In this video, we will discuss the Newton-Raphson method in solving for the root of a nonlinear equation. This method is an open method, just like the fixed point iteration method, and it utilizes the derivative of a function f of x. That is why very important consideration in using the Newton-Raphson method is your function should be something that is easy to take the derivative of. No, it's easy to differentiate. No, otherwise, no, if your function is very complicated and differentiating will entail too much work, no, then most probably Newton-Raphson method will be troublesome, no, to use. Okay. Now this problem or this method, no, utilizes the tangent line to a curve, okay, of your f of x, okay, such that when you create the tangent line to the graph of y equals f of x, for instance, so this is your y equals f of x, so the intersection is your x bar. So let's say this is my estimate of the root x sub k, and then corresponding is a point on the graph, okay, corresponding to x sub k, f of x sub k. So I can create a point on the point on the graph, okay, and then create a tangent line on that point and make it intersect with the x-axis. So the intersection of this tangent line with the x-axis gives my next refined estimate, x sub k plus 1. So that is how your Newton-Raphson method works. Okay, so the iterative formula, okay, for the Newton-Raphson method is basically the slope formula. No, recall that the slope formula is delta y over delta x. So you have 2 points on the tangent line. One point is x sub k, f of x sub k. The other point is x sub k plus 1, 0. Okay. So this point corresponds to x sub k plus 1, 0 on the x-axis. So if you use the slope formula as delta y over delta x, the slope here is represented by the derivative of f at x sub k. This is equal to f of x sub k minus 0 over x sub k minus x sub k plus 1. So our goal is to solve for an expression for x sub k plus 1. So we just manipulate this equation. So you have here f prime of x sub k times x sub k minus x sub k plus 1 is equal to f of x sub k. Dividing both sides by f prime of x sub k and solving for x sub k plus 1, we will arrive at the formula x sub k plus 1 is equal to x sub k minus the ratio of f of x sub k divided by f prime of x sub k. So this one gives us the iterative formula for the refined estimate using the Newton-Raphson method. So this one can be read as this, no? You have here the refined estimate x sub k plus 1 is equal to the previous estimate, no, minus the ratio of the function evaluated using the previous estimate divided by the derivative of the function evaluated using the previous estimate. So let us have an example. So this is the function e raised to negative x equals x using Newton-Raphson method with an initial guess of x not equal 0 up to a relative error of less than or equal to 20%. So if you may recall, this is a problem that we solved using fixed point iteration method. So this time, let's use Newton-Raphson method in order for us to compare, no, then the two methods, no, which one converges faster. Okay, so looking at the given, okay, we have here e to the negative x equals x. It is important to note that you need to start with f of x equals 0. Okay, so this is not yet f of x equals 0. Kasi you need to get the proper form or the proper expression for f of x. Okay, so with this, from e raised to negative x equals x, we have to transform this to raised to negative x minus x equals 0. Okay, to make it in the form f of x equals 0. And then from here, okay, you can now say that your f of x is actually equal to e to the negative x minus x. And then your derivative f prime of x is equal to negative e to the negative x, and then derivative of x with respect to x is just 1. So, basically, medyo simple yung ating f prime, no? Simpleng kuhanin, no? So, it will not give us a complicated function. So, our iterative formula, following our general form of the iterative formula, no? X sub k plus 1 is equal to x sub k minus f of x sub k divided by f prime of x sub k. So that will be x sub k plus 1 is equal to x sub k minus e to the negative x sub k minus x sub k all over negative e to the negative x sub k minus 1. So this is our iterative formula. So we will just plug in values here of your previous estimates, no? Doon sa right-hand side ng ating equation to get a value of the defined estimate. So for the first iteration, we note that your initial value is 0. So our value of the first iteration, x sub 1, is equal to 0 minus e to the negative 0 minus 0 divided by negative e to the negative 0 minus 1. But e to the negative 0 is just 1. Divided by negative 1 minus 1 is 2. Negative 1 half. Okay? And then may negative ka sa labas, so you have positive 1 half or positive 0.5. Our stopping criterion is relative error less than 20%. So we have to solve for the relative error. But actually, since 0 naman tayo nag-start, we expect that our relative error will be 100%. Okay? For the next iteration, iteration 2, x sub 2 is equal to, so same formula, no? Previous estimate, so we will be using 0.5 minus e to the negative previous estimate minus previous estimate divided by negative e raised to the negative previous estimate minus 1. So solving for this value, you will get 0.566311. The relative error for this iteration, so present value 0.566 311 minus 0.5 previous value over present times 100. So you have 11.71%, which surprisingly we already obtained. Okay, yung ating error that is less than 20%, no, na criterion. Okay, therefore we can now stop iteration. Hence, our x bar is approximately equal to x sub 2, which is 0.566311. Note that in our fixed point iteration, it took us more iterations, no, in order for us to get a less than 20% relative error. Okay, so mas madali tayo nakakuha ng root dito sa ating Newton-Raphson method compared to the fixed point iteration. And dun sa ating fixed point iteration, after I think 5 iterations, ang nakuha nating value is 0.60624 something, no? So ito naman 0.566311. And yet ito ay mas accurate dahil 11.71%, no? Mas mababa, no, yung relative error natin compared doon sa 17% na nakuha natin doon sa ating fixed point iteration method. Okay, but still we can see that ang roots na nakuha natin for both methods, Newton-Raphson and fixed point iteration, malapit naman kay yung values nila. Okay, so we can say that we are approaching the same root. Kasi there are times na if you have multiple roots, okay, pwedeng using another method, ang mangyayari is ibang root yung i-approach. Okay, depende kasi yun sa starting point natin, depende rin sa method na ginamit. Okay, pwedeng ibang root yung makuha natin dahil more than one yung root na available doon sa ating function or sa equation. Now let's have another example. You want to find one real root of x cubed minus 5x plus 1 equals 0 using Newton-Raphson method with initial guess of 0, accurate to 6 decimal places. So polynomial lang naman to, so madali lang siyang i-differentiate, no? So your f of x is already defined because f of x equals 0 yung form ng given sa ating equation. So your f of x, the x cubed minus 5x plus 1. So f prime of x is simply 3x squared minus 5. And so our iterative formula will be of the form x sub k plus 1 equals x sub k minus f of x sub k. So x sub k cubed minus 5 times x sub k plus 1 all over f prime of x sub k, 3x sub k squared minus 5. We do now our first iteration. Iteration number 1. Our initial guess is 0. So x sub 1 is equal to 0 minus 0 cubed minus 5 times 0 plus 1 divided by 3 times 0 squared minus 5, which gives us 0.2. So remember, 6 decimal places yung accuracy na kailangan natin, no? Iteration number 2. X sub 2 is equal to, so same formula, but we will now be using 0.2 as our input. So that's 0.2 minus 0.2 cubed minus 5 times 0.2 plus 1 divided by 3 times 0.2 squared minus 5. That this is equal to 0.201639. So I included 7 decimal places, no? Since our stopping criterion is accurate dapat siya to 6 decimal places. So, para meron tayong pasobrang isa. So, obviously, hindi pa siya nag-satisfy sa stopping criterion natin. No? So, we need to have one more iteration. So, using this value that we obtained from x2, we now have the third iteration, x3. x3 is equal to, so 0.2016393 minus quantity 0.2016393 cube minus 5 times the same plus 1 all over 3 times 0.2016393 squared minus 5. We obtain here x3 equals 0.2016397. So if you compare now, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Dun sa first 6 decimal places, parehas na sila nung previous. So we now say that this one is already accurate to 6 decimal places. Therefore, we can now conclude now that x bar is approximately equal to x3 after 3 iterations. This is equal to 0.2016397.